welcome to our exploration of Chapter 6 of the Book of Lying
Yeah.
by Judea Pearl and Dana McKenzie.
Okay.
This summary and podcast have been prepared by Amira Faye. You ready to dive into some seriously mind-bending paradoxes?
Absolutely. Chapter 6 is like a carnival funhouse for our brains,
Okay.
showing us how easily our intuition about probability and statistics can be tricked.
All right, let's start with a classic, the Monty Hall problem. You're on a game show, 3 doors, one has a car, the other 2 have goats. You pick a door. The host, who knows what's behind each door, opens a different door, revealing a goat. They then give you the option to stick with your original choice or switch to the other closed door. Most people would think the odds are 50-50 at this point, right?
That's the natural assumption, but surprisingly, switching doors actually doubles your chances of winning.
Hold on, are you saying most people would actually be hurting their chances by sticking with their gut instinct? Why is our intuition so off here?
Because our brains crave causal explanations. We see a pattern and assume there must be a cause. But with the Monty Hall problem, the host's action of revealing a goat creates a kind of informational bias. It's not about a direct causal link between your choice and the car's location, but rather about how the host's knowledge skews the probabilities.
So it's like the host is giving you a secret hint, even if they don't mean to.
Exactly. Think of it this way. Initially, when you picked a door, you had a 13 chance of being right.
Okay.
That means there's a 23 chance the car is behind one of the other 2 doors. When the host reveals a goat, they're essentially concentrating that entire 23 probability onto the single remaining closed door.
Okay, I think I'm starting to see it. But this idea of the host's action creating a spurious dependence, that still feels a bit abstract. Can you give a real-world example?
Imagine you're analyzing a survey about exercise and heart health. You might find a correlation between owning a treadmill and having heart problems. On the surface, this might make you think treadmills are bad for your heart. But what if the survey didn't account for age? Older people are more likely to own treadmills and more likely to have heart problems.
So the treadmill isn't causing the heart problems, it's just that both are more common in older people.
Exactly. Age is the hidden variable, what we call a collider in causal diagrams. It's like a fork in the road where 2 paths converge. By focusing on people who own treadmills, you're essentially conditioning on that collider, and that's what creates the misleading correlation.
So we need to be really careful about drawing conclusions from correlations without understanding the full causal picture. It's like we need to put on those detective hats and look for any hidden variables that might be skewing the evidence. But this craving for causal explanations can also lead us down some surprising paths, as we see in Bergson's paradox, right?
Precisely. Imagine you're studying 2 diseases that are completely unrelated in the general population, but when you look at hospital admissions, it appears that having one disease significantly increases your risk of having the other.
So are you saying even if a study shows a strong link between 2 things in a specific setting, that link might not actually exist in the real world?
That's the essence of Bergson's paradox.
Okay.
The hospital environment itself is acting as that hidden collider again. People are more likely to be hospitalized if they have either of the diseases, creating an artificial association between them.
So how do we avoid falling for this trap? Should we just be skeptical of any study that involves hospitalized patients?
Not necessarily.
Okay.
The key is to be aware of the potential for selection bias. Researchers can use various statistical techniques to adjust for these biases and get a more accurate picture of the true relationship between variables.
This reminds me of a study I read about that found a surprisingly high frequency of bone disease among hospitalized individuals with respiratory disease.
That sounds like a classic example of Bergson's paradox in action. Just like with the treadmill example, the hospital setting creates a spurious correlation between 2 conditions that are actually independent in the general population.
So we need to be careful about generalizing findings from specific settings to the wider world. It seems like we can't just take correlations at face value. We need to dig deeper and consider the causal pathways involved.
Exactly, and that's where the power of causal thinking comes in. By mapping out the causal relationships between variables, we can avoid these pitfalls and arrive at more accurate and insightful conclusions. Now, ready for another paradox that really twists our understanding of cause and effect?
Bring it on. I'm starting to enjoy having my assumptions challenged.
Let's talk about Simpson's paradox. Imagine a doctor is testing a new drug, let's call it drug D, to reduce heart attack risk. Early research suggests it's beneficial. However, when the doctor analyzes the data for men and women separately, a strange pattern emerges. Men who took drug D actually had a higher risk of heart attacks, and so did the women who took it. But when the data is combined, ignoring gender, the drug appears beneficial overall. How is that even possible?
Wait, so it's harmful for both men and women individually, but somehow beneficial for the whole population? That seems completely backwards.
That's the paradox. It's like saying if wearing a raincoat keeps you dry in the rain and keeps you dry on a sunny day, then it should always keep you dry. But that logic breaks down because you're more likely to wear a raincoat when it's raining in the first place.
So in this case, it's not the drug itself that's the problem, but something else influencing who takes it.
Exactly. Gender is the confounding variable here. Men in the study were more likely to have heart attacks in general, and they were also less likely to take drug D. Women, on the other hand, were more likely to take the drug, potentially because they were more health conscious overall.
So the drug is being unfairly canalized because it was primarily taken by a group that was already at a lower risk of heart attacks.
Precisely. This difference in drug uptake between men and women skews the overall results, masking the drug's true harmful effect. We call this Simpson's paradox. It highlights how crucial it is to consider confounding variables and understand the causal relationships at play.
It makes you wonder how many times this kind of misleading correlation has slipped through the cracks, especially in fields like medicine where the stakes are so high.
It happens more often than you might think, which is why understanding causal inference is so important. It's not enough to just crunch the numbers. We need to think critically about the data-generating process and the underlying causal structure.
So how do we untangle these messy correlations? Can causal diagrams help us here too?
Absolutely. In the drug D case, a causal diagram would show gender as the confounder, influencing both drug and heart attack. To get a true picture of the drug's effect, we need to stratify the data by gender. That way, we're comparing apples to apples and oranges to oranges.
So in this scenario, looking at the aggregated data actually gives us the wrong answer, right?
Exactly. It's a powerful reminder that how we analyze data, whether we aggregate it or stratify it, depends on the causal structure of the problem, not just the numbers themselves. Sometimes aggregating data is the right approach. Other times it can lead to completely misleading conclusions.
Can you give an example where aggregating the data is the correct approach? I'm trying to wrap my head around when to do what.
Let's say a study is looking at the effectiveness of drug B in reducing blood pressure and also whether it has any impact on heart attack risk.
Okay.
The results show that people who took drug B were less likely to have a heart attack. In this case, aggregating the data actually does accurately reflect the drug's effect.
So why is aggregating okay here, but not with drug D? They both seem like they have multiple factors at play.
The difference lies in the causal structure. In this scenario, blood pressure is a mediator, not a confounder. It sits on the causal pathway between drug B and heart attack. Drug B lowers blood pressure, which then reduces the risk of heart attack. If we stratify the data by blood pressure, we'd actually be breaking this causal chain and getting a misleadingly low estimate of the drug's effectiveness.
Okay, so it all comes down to understanding whether a variable is a confounder, like gender in the drug D case, or a mediator like blood pressure in the drug B example.
Precisely, and that's why those causal diagrams are so valuable. They provide a visual roadmap for analyzing data and help us avoid these common pitfalls.
This is really highlighting how easy it is to misinterpret data if we don't have that causal lens. It's like those optical illusions where your brain tricks you into seeing something that's not really there.
That's a great analogy. And just like with optical illusions, once you see the trick, it's hard to unsee it. Once you start thinking causally, you'll be amazed at how many misleading correlations you spot in everyday life.
It's like those moments when you're trying to solve a riddle.
Right.
And you're so focused on the wrong clues. And then someone points out a simple detail you overlooked, and suddenly the whole thing makes sense.
Exactly. And that's what's so exciting about this causal revolution that Judea Pearl has brought to the forefront. It's giving us the tools to move beyond those misleading correlations and see the world through a clearer, more accurate lens.
I'm curious, though, these paradoxes seem to pop up a lot in research settings. Can you give some examples of how they might show up in everyday life?
Absolutely. Think about how people often misinterpret data about lifestyle choices. You might see a study showing that people who drink red wine live longer. But what if those people also tend to have healthier diets and exercise more? The red wine might not be the cause of their longevity, it's just correlated with other healthy habits.
So it's like the treadmill example. There's that hidden variable overall healthy lifestyle that's driving the correlation.
Exactly. Or consider how people perceive risk. You might hear that a certain neighborhood has a high crime rate and assume it's inherently dangerous. But what if that neighborhood also has a higher population density, leading to more opportunities for crime? The neighborhood itself might not be the cause of the crime, it's just a factor that influences the likelihood.
These paradoxes really make you think twice about jumping to conclusions based on surface-level observations. We need to be more like detectives, digging deeper to uncover the real causal story.
That's a great way to put it, and the more we understand these paradoxes, the better equipped we are to make informed decisions in all aspects of our lives.
So before we wrap up, what are some key takeaways our listeners should remember from our exploration of these mind-bending paradoxes?
First, correlations can be deceiving. Always ask yourself, why might these variables be related? Is there a plausible causal explanation, or is there a hidden collider or confounder at play?
Right, correlation does not equal causation. We need to remember that those catchy headlines often oversimplify complex relationships.
Second, consider the data generating process. How is the data collected? Are there any biases that might be skewing the results? And always be wary of drawing sweeping conclusions from limited data sets.
It's like that saying, statistics are like bikinis. What they reveal is suggestive, but what they conceal is vital. We need to look beyond the surface and think critically about the context.
And finally, embrace the power of causal diagrams. They can help you visualize those complex relationships between variables, identify potential confounders, and avoid the pitfalls of those statistical illusions we've been discussing.
It's like having a roadmap to navigate those tricky statistical waters. Now, I know we've covered a lot of ground today, and it might feel a bit overwhelming.
It's true that these concepts can be challenging at first, but that's what makes them so rewarding to explore. The more we learn about these paradoxes, the more we realize how much we don't know. And that sparks a curiosity to keep learning and questioning.
Speaking of learning and questioning, we've only just scratched the surface of Judea Pearl's work. In the upcoming chapters of the Book of Why, we'll delve even deeper into the world of causation, exploring concepts like inventions, counterfactuals, and the due calculus.
These tools will allow us not only to understand why things happen, but also to make predictions about what might happen if we intervene in the world around us. It opens up a whole new realm of possibilities for how we can use data to solve problems and make better decisions.
So, to our listeners, we encourage you to keep those causal glasses on. Look for those hidden confounders and colliders lurking in everyday life. And keep questioning those correlations. As Judea Pearl reminds us, the ladder of causation has 3 rungs: seeing, doing, and imagining. We've taken the first step by seeing those causal connections. Now let's continue climbing that ladder and explore the power of doing and imagining.